Alrighty, chapter 10 uh, deals with parametric, polar, and vectors. Except for the application of calculus to these things, the only thing that's really new is what will come up in a couple of sections called vector value functions. This chapter looks long and daunting, but the great thing about this chapter is that a lot of the sections, including 10.1, are review sections. So we'll have a review section on parametrics, and then we'll apply calculus to them in 10.2. We'll have a review section in 10.3 on vectors, and then in 10.4 and 10.5 we'll apply calculus to them. 10.6 we'll have a review section on polar, and then we'll apply calculus to them. And then the last two sections of the book are just review on conic sections and polar conic sections. So there's a lot of review in this chapter, and since we went through this in great detail last year, you should feel fairly confident with the vast majority of this. We won't spend a whole lot of time dealing with the spend a whole lot of time dealing with the review, but I figure a video or two in order to get us back up to speed, remind us what these things are all about, is something that's worth doing at least. So let's actually talk about the logic behind parametrics. Now, if we think back to Algebra 2, I know it's been a long time, but it was a little more than 2 years ago that we started talking about quadratics. Okay, and then we had quadratic word problems. And so if you were trying to optimize how much money do you need to charge per cookie at the cookie stand in order to maximize profits, right? And you would get something like this, right? And it would be y in terms of negative ax squared plus bx plus c or something like that, right? And whatever it is, you recognize the fact that y was dependent upon x, right? So if you wanted y, or whatever it was, if it was revenue per price of the cookie, and it was negative a p squared plus bp plus c or something like that. It didn't really matter what it was, input and output. You basically had two variables. You had one which registered, your p values, and one which registered your revenue values. Okay. We got a little bit closer to parametrics when we started applying quadratics to gravity, right? And so you had something more akin to the position of something had to do with negative 1/2 g t squared plus v naught t plus s naught, or it was either s or h. S is standard for position and h for height. And you still had, it looked something like this, and it was a downward-facing parabola, and you had, your t-axis and your s of t-axis. But this sort of hints towards what parametric is all about, because height was dependent upon time. Well, let's say that you actually did fire a projectile, and when you do fire a projectile, like, a cannonball from a cannon, it actually does make a parabolic arc, okay? And so, you have your cannon over here, spokes, and boom, right? Okay, not an artist, never have been. Okay, well, here's the thing. This no longer is time. This is actually your horizontal displacement, right? Horizontal distance, displacement, whatever. Okay? And then, of course, your vertical axis is still your height. And so, you have your vertical displacement. We'll abbreviate it like that. And we'll call this y, and we'll call this x. Well, in a sense, your output, what usually your output, your y, is not really dependent upon x. I mean, it has a relationship to x, but how high the cannonball flies is not dependent upon how far it flies, okay? Both of them are independently related to a third variable, which is t. where is the cannonball after 3 seconds? Well, that where question means I want an x and a y of where it is. So you have x and y both dependent upon a third variable, t. But t doesn't actually show up anywhere here. T is not visible in the graph. It is sort of like the hidden variable that determines the two visible variables, both x and y. And that's basically what's going on when we're dealing with parametrics. And it's kind of, you kind of get a hint about parametrics before you actually get there in pre-cal. Because you've seen it before. You have x and y ordered pairs around the unit circle, both dependent upon that third variable, which happens to be theta. There's a minor difference there in the fact that theta is actually somewhat visible, but it's that same sort of idea that you want x and y dependent upon a third variable, most often t, okay? So that's kind of the logic behind it. My vertical axis is no longer my independent, and of course my axis, is no longer my dependent variable, being dependent upon my horizontal axis variable. Both x and y, both my horizontal and my vertical, are dependent upon the parameter, the third variable, which actually isn't visible, okay? So what we're going to do right now is we're going to actually remind ourselves exactly how to graph these things, okay? And so let's say that we're given, let's start off with a rather easy one. How about x is equal to 2 plus 3t, and y is equal to negative 1 minus 2t, okay? Well, it should be very, very easy to discern that this is a linear function, okay? And if you can't see that right now, once you get back up and running and become more comfortable with parametrics again, it actually should come back to you, okay? And what I need to do is, instead of dealing with a t-chart, it's kind of related to a t-chart. I mean, it is a table of values. I'm going to start plugging in just values for t and getting both x and y measurements out. So if I plug in 0 for t, I'm going to get what? Both of these are going to be 0. If I plug in 0 for t here, I'm just going to get 2 for x. If I plug in 0 here for t, I'm going to get negative 1 for y. So 2, negative 1. Okay, well let's plug in 1 for t, okay? If I plug in 1 for t, then I'm going to get 5 here, okay? If I plug in 1 for t here, I'm going to get negative 3. So 5, negative 3, okay? Well, let's go ahead and plug in negative 1. If I plug in negative 1, I'm going to get a negative 1 here for x, and I'm going to get a positive 1 for y, okay? Well, that gives me something like this, okay? Now, here's the thing. Because both x and y are dependent upon a third variable t, I can actually show the motion, right? I can actually show the motion because this right here, this point where was t is equal to negative 1, this point right here was where t was equal to 0. This point right here was where t is equal to 1. So as t increases, which way is this graph moving? Well, it's obviously moving this way. So you can draw little arrowheads along the graph in order to show the motion. Now, that's the advantage that this has over what would otherwise be a very easy linear equation. Now, obviously, the slope here is negative 2/3. That kind of makes sense because y is changing by negative 2 as x is changing by positive 3, okay? So that means that my slope is negative 2/3. And of course, I could just take this right here. This is an ordered pair. When t was equal to 0, that was an ordered pair. So my x1, y1 is 2, -1. So, you know, I could describe this in terms of y minus y1 is equal to m times x minus x1. That is a perfectly legitimate equation for the same line, which was the graph of my parametric set of equations up here. The advantage that the parametrics have, however, is that I can actually tell A, which direction it's going, and B, when the graph is at a particular point. And those are two rather important things to be able to do for certain physical scenarios that can be represented by parametric equations, okay? And so when you're being asked to graph parametric equations, you could actually be asked to show the directionality of that particular graph. Now, let's go ahead and do an example of a conic. Now you may remember that x is equal to 2 sine t, or actually we can call it theta, it's not a big deal. Y is equal to 3 cosine theta. Okay, well, this is a rather easy conic, so we'll just go ahead and turn this one out rather quickly. Okay, so when theta is equal to 0, x is going to be equal to 0, and y is going to be equal to 3, so here. And that occurs when theta is equal to 0. Okay, well let's deal with theta is equal to pi over 2. When theta is equal to pi over 2, y is going to be 0, and x is going to be 2. Okay, and so that right there happens when theta is equal to pi over 2. Down here is where theta is going to be equal to pi, and over here is going to be where theta is equal to 3 pi over 2. So this right here is an ellipse, okay? And it is obvious from my plotting of points that the directionality goes this way, okay? Now, how is this going to be different from, okay, let's say we have x is equal to 2 cosine theta, y is equal to 3 sine theta. Now this is going to give me an identical looking graph. Okay? Because when I plug in 0 for theta, I'm going to get 2, 0. The only difference between this one and this one is when. At what theta value does it arrive here at 2, 0? For this original one, it arrives at 2, 0 on the xy coordinate plane when theta is equal to pi over 2. For this one, it actually arrives there at theta is equal to 0. Okay? So you can actually have two distinct representations of the of a graph in terms of its parametric equations, but they won't be identical in terms of when, at what value of the parameter the graph arrives at a particular point on the xy coordinate plane. And that's the significant aspect. That's one of the payoffs of using parametrics over what we usually refer to as Cartesian, xy, without the parameter. Okay. In the next video, we're going to review how to eliminate the parameter, how to go from something like this to what we're used to in terms of rectangular, and also going the other way, being given a graph, or being given a description of a graph, or being given the rectangular Cartesian notation, formulation, equation of a graph, and actually turning it into parametrics. And that, of course, will take us through one more video, and then we'll actually get on to 10.2, which is the application of calculus to these. And it actually really isn't that big of a deal, and we ought to be able to breeze through that in maybe about 3 or 4 videos. So be looking forward to that. If you have any questions, as always, please do email me. Bye-bye.